Cool. So what I would like to, so welcome to everyone that is only able to join in the recording. Sorry that you couldn't join live. Yeah, apologies for that. And hopefully we won't have the same technical difficulties next time. To everyone as well, thank you for coming in person. And the paper that I want to talk about this week, it's a bit of a monster. And if any of you made it through, well done. I'm not sure I made it through really, but I think there's some interesting ideas to talk about here. And yeah, maybe I won't cover everything that they cover in the paper. Where's my mouse? Can't get it on this screen. Okay, cool. Okay. So what this paper is about is a way, I guess, of thinking about deep networks and trying to conceptualize a bit what they're doing inside. So I think there's definitely merit to the stuff that they talk about. It will only refer to a subset, I think, of deep neural nets, but it's a large subset. And I guess the top line thing is that what they do with that way of thinking about deep nets is to try and characterize what the net is doing underneath, what it's able to say about the input space, and something then from what it's able to say about the input space, what it's doing to those subsections of the input space to get maybe a classification, a regression, whatever it might be. And from that, you can start to infer how it's making its decisions, if you like. At least that's what they posit here. So it's quite a big statement, and that's why I picked this paper, so we could start to, I guess, think about whether that's a good statement to make or not. And yeah, I think the right place to start is to talk about some terminology that they use. So the big hitter is max affine spline operators, right? And I think it's worth just going over what each of those bits mean, so we can talk about them a bit better. And you know what? Since it's just us in the room, I probably will use the whiteboard. So I'm going to unblur my background on the recording. So we can look at the whiteboard. So a spline, so say we've got a function. We've got a 1D function. Maybe it looks like this. A way to often with these, often what we're trying to do with a function like this, maybe it's really complicated, maybe we don't know exactly what it looks like. We're going to try and approximate that function. And a way to do that approximation is to find kind of regions of the input space and find a more simple function that is good at approximating this more complicated function within that region. So, you know, maybe we're allowed to have polynomials or something, and our approximation function maybe it looks like this in this region, or we get something steeper up here, but it doesn't do so well over here, and we get something really quite flat and linear over here. But we got through, the point being, the splines are the different functions in the different regions of the input space. So that's what a spline is.
it would also have to be, I think, moved or AC French for not that.
I think, yeah, so continuity of a spline approximation is, I don't think given, but like you can say what I want from this spline approximation is that it is continuous. And so, yeah, rather than your splines going like that and then having this discontinuity here, you can say, actually, I don't want that. I'd rather they met at the intersection points. And then, yeah, I guess the final piece of what is affine? So affine is just a straight line with an offset. So so maybe instead of 3 functions that do whatever we want, like they're curvy or they're polynomial somehow, we have 3 straight lines. So I guess you'd write that like mx plus c or whatever. This is an affine function in 1 dimension, but you can have obviously a multi-dimensional input space, and your affine function would be a matrix. Well, not matrix, sorry, just a vector, right?
It's effectively a plane, but
yeah, so it's a hyperplane in that space. Yeah, and with all of this preamble, we're trying to get at something one-dimensional. So this function is like in the real numbers. When the O of the operator just means like what we're outputting is going to be a vector, right? So it's going to, instead of having like one value, it's going to have loads of values in the vector. So we're going to be approximating over many dimensions. Maybe that's the way to put it. So I think that's affine, spline, and operator. The max part is quite interesting. So you can kind of imagine if I drew a function that was a bit less nice, and by nice I mean it only curves in one direction. So if I drew a function that's like this, my lines might do something. Maybe my lines go like this, and all of a sudden. Okay, maybe it's better to walk back there. So in this instance, if we draw our lines, for any point in the input space, all I need to do is evaluate all of these affine functions at that point. I evaluate this one and this one and this one, and then my best approximation is the maximum. And that works because this is like a ball. It's convex. But if we were to have a non-convex function, that wouldn't work. And that's quite important for a lot of the results that come in the paper. But yeah, hopefully now we've got all the component parts to understand what a max affine spline operator is.
So max thing means it's some space, the maximum value, or
it literally in the real numbers. So it will, for each of these, you can imagine we've got this 1D function coming out, but instead of the input space also being 1D, it's like some crazy high dimensional space. But we can,
maximum.
Yes.
The maximum as in this example that we did for the function is approximated from below, but those also be true to function would be approximated from above.
Yeah, I think convexity will just mean that when you draw your splines like this, when you draw your functions, it's always the maximum one that you're after. That the complexity of the function tells you that, I think. This is that's what I understand anyway. I'm not totally sure, but I think because the function is convex, the maximum spline, the maximum result is the spline you're after. And in a way, that the nice thing about this is this actually informs your partition of the input space, because you'll get a bunch of affine functions, and these places where they cross will then map down to something in the input space, right? And a lot of the paper is like, actually, let's make something of what is different about this compared to this.
Did you start with the family of these functions, or?
Okay, now it's time to go to the paper, I think. So here, what they're saying basically is every layer of a deep net is, you can frame it as a max affine spline operator. These results are kind of just stated, but if you look here, so convolution is a affine transformation. Fully connected layer is an affine transformation. And then, sorry, go ahead.
Yeah, the other thing is that affine is the thing in there, right? But
Yeah.
the fully connected layer by itself is containing the activation.
So it depends what activation you use. That's what they say here. So if you use, for instance, ReLU, then they show that it can be framed as, and I actually have a little example to show about ReLU. That they show that it can be framed in this way, and also max pooling. What they do also say though is that, I'm trying to remember exactly where they put it, but some of the activation functions are not convex, right? So sigmoid, non-convex, hyperbolic tangent, non-convex. So you can't do some of this stuff, but they do have results in here that like address that. I don't think we'll get to that today. They're talking more about approximating when those are like pieces of the layer internal to the network. But essentially what they say here, yeah, so they're talking about softmax activation. But the interesting thing, I guess, is because that's right at the end, you can say certain things about what's happened inside the rest of the network without worrying too much about what's happened at the end. And I think I'm going to sort of skip a bit and go to a picture that I have. So my main complaint about this paper is that I think I learned a lot more watching one of the authors talk about it on YouTube than reading. So yeah, essentially here is where they're talking about breaking down the layers of the network into the different transformations. And each one of them can be framed as one of these. Wait, let me see if I can find the result about the fact that it's a MASO. Yeah, here we go. So yeah, they make a couple of propositions where they show, and the proofs to these are in the appendix. I don't think it's worth going into this right now. But essentially, yeah, these. So what he's saying here is that the fully connected layer is a max affine spline operator by the fact that it's literally one affine operator. And because these if you have a piecewise affine convex activation function, then you can show, well, you can see that it would be a max affine spline operator. And yeah, with those two results, they also have I think there's a well-known result that compositions of max affine operators are themselves affine operators. So, or piecewise affine, sorry. So if you partition your input space, you're going to just be doing some sort of linear transformation plus a bias to get to your output. As long as you know which section of your input space you're in, that's what you're going to be doing. And I think that's the main kind of thrust of this paper. So they're saying, if you look at all the parameters in the right way, you can reframe the whole problem as understand what part of the input space you're in, and then look up what matrix you should be multiplying everything by, do that multiplication, and then that's going to give you the inputs to your softmax layer. So let me.
Would that already be the output stuff?
They can't do the last, because of the non-convexity of the softmax, you can't do that last part. But no worries.
So the complexity comes then, which is then be translated then in the input space in final position.
Yeah. So I think maybe there's some interesting pictures to look at now. So I think first let's talk about a toy example of a layer. So maybe what we have is some fully connected layer on a 2D space plus a ReLU. And the output of the whole layer, I guess you can say, is going to be this ReLU on the weights plus the input, the weights times the input plus the biases. And we've got these five outputs. So each one of these is going to have some place where this bit is 0, right? And so the ReLU is going to change from one of its splines to the other one of its splines. Yeah, so each of these is going to define a plane in the input space.
So those are each one represents a position.
Yeah.
What does the inside have to be 0?
I think because this is where we're switching from one spline in the ReLU to the other spline. Does that make sense?
Saying that if it's lines together, but not maybe some sort of max line, so it has to be at that point. It's already obvious that it's obviously there.
It wouldn't always be at 0, but I think the point is it's when you're switching from one spline to the other. So
only doesn't, let's say that value of one value. Well, yeah, sorry. Not sure.
So I'm not totally sure what this equals 0 is. As I say, I've stolen some of these pictures from the slides from Richard's Balamek. But this needs to be 0 because we're switching from, I guess, one regime here to the other regime. Does that?
But there's a single value, right? But they go from one value function with one set of functions. I would have just thought that the value at that point for the exact value must be the same when it's in 3, but not that they have to be 0. But
so I guess the points in the input space where this bit's going to be 0 are defined by the weights and the biases, right?
yes.
Yeah. So it will we can see that because of we're getting 5 kind of equations here, 5 2D linear equations that we're defining 5 straight lines, and they're going to cross and they're going to partition the input space. That's what he's getting at here. And so this is one layer, right? And we've got a bunch of straight lines. We've crossed them all over with each other, and they partition the input space. Have we learned anything? Probably not. So the next thing to do is kind of stack on the next layer. And you can do a very similar thing. So because you know what the MASO is, you know what the slices are going to be to the input to that layer. And then you can pass those slices all the way back through to the input space as well. And they're gonna bend a bit because of the things that you're doing with your activation function and your weights and biases in each of these different partition zones on the first layer, but you will end up partitioning your input space even more. And so on and so on, right? Like as you get more and more layers, you're going to partition everything more and more.
So it takes the existing and partitions it more, and then also bends it as well.
Yeah, so each of the sort of boundaries of the splines isn't going to be a straight line anymore because of the different things, the different weights and biases that are applied in the different regions. So let me think where we're going next. So yeah, essentially, you will have sliced up your input space into loads and loads of regions. And it's a shame I haven't got one more picture on here, but the example that he uses in one of the videos is about a binary classifier. So maybe this is like a 3-layer binary classifier. And the final layer is going to have one decision boundary, basically. And he actually draws then on this layer 2 diagram, a 3rd layer with this quite complicated decision boundary, because it's bending and changing through all of the different partitions. But he's kind of shown that you can chop that input space into 2. And if you can say which part of the input space, and you can say what your class is going to be. Now, that's obviously a bit of a toy example because the problems that deep networks do are a lot harder than binary classification a lot of the time. But I think it's a nice visual. So I would go and search out that visual if I were you.
Almost like each space could be like a binary representation of.
Say again?
Each space, each segment of the wiki could be could be represented by a binary number, diamond left or right of that plane, left or right of that plane, left or right of that plane. Mm. Sort of discrete version of this.
Yeah.
Space, right? So
I think the final thing that's kind of interesting is to say, so if we go back to the paper, so I'm kind of going to skip section 4. They do examples of decomposing common networks into these formats, and then talk a bit about non-convex stuff. But then section 5 I found quite interesting. So I struggled to get it at first, but I think I kind of understand what it's getting at now. So what they are saying is that dependent on where the where the input is in the input space, what the network is going to be doing is trying to match a template, basically. And they make then some claims about memorization. They make some claims about whether what it's doing is actually trying to memorize areas of the input space, and then try and say some stuff about generalization that I don't really know so much about, but I think trying to work out this section is interesting. So this equation, what they're saying is let me work out which bit I'm trying to talk about. So depending on, I think this is supposed to be one matrix. Yeah, so this whole thing is a matrix. Annoying notation, but fine. And they're saying, okay, where am I in the input space? And give me the matrix that refers to the affine transformation that we know we have in this partition of the input space. And do the matrix multiplication, do my biases as well, and give me some sort of, give me the outputs that come before my softmax. So I think, yeah. And then they're saying, really what we have here then is we're going to get the largest element, and that's going to be our class, because if we're applying a softmax, all you care about is which one's biggest. So they're kind of saying,
with the largest error that can happen, then it must become the very last layer, right? So the partitioning of the input space, the partitioning is already happening.
so the partition,
Yeah.
you can pass the partition of every layer all the way back through to the input space.
Yes. Principle of partition the input space already made very first layer into boxes that will define a path to your layers, right? So, and then, of course, if these boxes are small enough, then
Yeah.
they probably would represent the class. So,
Well, so the interesting thing is, yeah, so essentially what they're saying here is we're looking for the row of this matrix that is most similar somehow to our input image, because what we're doing here is kind of like a cross product of the rows. So you get your image and you cross product it with each of the rows, and whichever one's biggest is going to give you your biggest value, and that's going to be the class that you output. And there's some diagrams here where they're basically like looking at the cross products of the different, trying to visualize the rows of this matrix in the same way that you would visualize the image, and then giving the cross products here. And I couldn't really see this in this diagram. They all look kind of similar to me, but I think what this is essentially showing is that the cross product of this, well, this is like a negative, a positive of this image, so you're getting quite a large cross product, but these two are negatives. So it's somehow optimized so that the filters for the non-positive classes are like extremely opposite to the image in those regions. So,
but that means also sort of generally say that you have 2 points that sort of map to the same activation. That could be fairly far away in that space, right? So that you think that these.
So you mean like 2 plane images of a plane that look different?
That once it's trained, that the actual direction of your layers probably can be rotated to some extent, or can be compensated out for different rotations as long as the further layer down are mapping to the same thing, right? So that's why maybe these don't look necessarily natural, because only the combining gets up in the
potentially. I think so. That the way that I've come to understand what they're trying to get at here is that like you've sliced the input space and it might only have one example in, right? And if it only has one example in, then you're almost certainly going to end up with something like this, where your template that you're trying to match is almost exactly the image. But they also show some stuff on CFAR 10 where they have this template. And so that I'm kind of imagining the partition has all the vertical 8s. It's all the 8s that are like in a vertical orientation. But there might be some other region that has all the 8s in a more left orientation, or that are horizontal or something. So yeah, I think this is a really interesting result in what it tells you about the input space and what the deep net can tell you about the input space. And yeah, I guess a bit of an idea of what is happening underneath, or at least a frame through which to look at what's happening underneath. Yeah, I think that's mainly what I wanted to talk about. It's kind of different to normal because I'm not going to talk about results or anything. And I would really encourage you guys to go and watch the YouTube videos that the second author on this has done, because I think he's like the lab leader almost, this guy. And he has a lot of nice pictures that I've stolen some of, but haven't stolen all of them. And I think he talks through things in a very clear way. One other interesting video, actually, while we're here, was this one. So maybe this is kind of interesting as well, because it's very tangible with the 2D input space. So you can see, oops, what we're trying to do here is a four-way classification. And we are training, I think, for 4 epochs, right? And you can see on the left, like this initial layer, the first partition of the input space, everything's going through 0, everything is crossing, and it's not like maybe a very good partition, not helping to split up the data very much. And then we start to move, and as you move through the training rounds, all the crosses, all the intersections move apart, and the partitions maybe somehow become a bit more meaningful. Like, we obviously haven't got there yet, otherwise one layer would work to classify stuff, but
look up, like what this is the first thing. You essentially could roll back and take the very last all the way up to the front.
well, this is what
So, yeah, exactly.
this is kind of what's going on.
But would you then only 2 steps, right? The first step of translating from the first to the very last step, which must be linear because it's a sort of combination of linear steps. If you have small enough parcel,
Yeah.
then either you already have figured that your results in a very small space, so you know what to get, or you have the last one, the activation. That could potentially reduce the complexity quite a bit, no?
I think potentially. I don't know how large. Well, I guess the point is, each of these individual regions is going to have a set of, like, it's going to have a matrix and a bias set. So the more regions that you have, the more complicated this becomes, because you're going to have to evaluate all of them and then find the maximum.
But then again, because the number of
Actually, no, you can't even do
in
that.
order to cut the space in many different pieces, my matrix is going slower. I have more. And so you might not have to store that many.
If there was a way for you to say which region of the input space you were in, easily.
Probably could be done.
Yeah.
Right? It would be, well, could be making both the basis by which side on which plane you're on. But you're right, then it's very much on the number of operations. But
Yeah, I just think it's kind of crazy when you look at it, that the shape that it's drawing here. You can definitely see how that second layer is able to use, I think, the partitions that are made here to bend its own partitions.
If I would zoom in, I would still see linear.
Yeah, so each of these is linear within one of these partitions. And you can kind of, I guess, maybe see that from here. I feel like this is quite low res, but
The second one, that's the second layer. Then what's the difference with the third one?
so the third one is just showing the whole partition of the input space. So this one is like showing the classes, if you like, the partition of the classes from the final layer. And this one is showing all of the different shards of the input space. Yeah.
Okay, when it goes all the way back.
When you've taken it all the way back from, so it's just superimposing this on this.
Yes.
Yeah. So yeah, I think it's an interesting paper. I definitely encourage you guys to go and watch the YouTube videos. I heard about this on Machine Learning Street Talk, and I was like, what is that? It sounds weird. And it is pretty weird. And I think like we've only kind of just scratched the surface of this paper. It's a massive paper where they talk about trying to leverage some of what they found here to make training better. And they seem to show that they're able to do that, which is really cool. So I wonder if there'll be any more things that they manage to make better or understand from looking at things in this way. Yeah. Any more questions?
Was that the main thing to find out that training or any other, I guess, improvement on inference time?
So it's a good question that and it's kind of similar to what Arvid was asking. I don't know if they show it here. The main thing that he speaks about is about kind of understanding what the network is then saying about the input space. So it's more like using networks as a tool to understand the input space. Yeah. So rather than it being about increasing accuracy or making training time faster, it's more like what can we say about what this trained network is doing or what it's saying.
So it might have a standardization, because they say that each layer, essentially what really matters is only which you end up in not the number of or below that.
Yeah. I can't think whether it would. I think, like you say, it really depends on how many parameters your network has in the first place.
For example, the question exactly how many quantitative steps we need in order to have like a n layer network reasonably well approximately before we can get bound, but we know really function this moves so that the maximum error at the end can be only this. So
Yeah.
probably could give a smart and come up with something that actually give you some estimate. Because this is like a simple problem, and at the end of the day, you look at it and see, yes, there are 4 regions, so somehow a very small number must be baked in there somewhere.
Yeah. Baked into the network.
Final solution.
Yeah. Yeah. Cool.
And since I was saying, you can run a big network on some input space,
Mhm.
and then do this analysis, and it might allow you to see some of that. And then you.
Yeah. So there's this tool that they, I think the first author is making that's like it's supposed to let you visualize what a network is doing to the input space. How you do that on image, like the space of images, I don't know how you visualize that, but
Also, paper it was about training on CPUs, where you can essentially do more like a lookup based thing, right? And this might actually be that.
yeah.
Essentially, have you CPU by lookups might go better one.
Because I guess that kind of is what you're doing. You're looking up a matrix and then you're doing that matrix multiplication once.
Yeah, or looking at your reproduction by multiplying this, so I don't make.
Unless you could find some way, yeah, I suppose you are. If you could find some way of defining which region you're in a like do all the computation intensive stuff
Yeah.
first,
Exactly.
that lets you map from an image to where it is, what region it's in.
Exactly. That's like the map from the past base to the very first to the very last day.
Yeah. Yeah. Cool. And yeah, some of you guys weren't in the room at the start, but if you want to present anything, want to talk about anything in Paper Club, please, yeah, just I think either say on the meetup or let Peter know or let me know. Dan at mplan.io. It'd be cool if you guys want to talk about something interesting.
Anything, you should on paper.
Yeah, absolutely. Anything. I was on the fence. There was a paper about like how the availability of hardware is very heterogeneous. So like people are going to get forced down a certain route in machine learning research because of the type of hardware that's available.
Yeah.
So yeah, if you want to do something that's more about the politics of machine learning, then yeah, please do.
I guess what the big problem now, like, they want to track people
Mm.
because it's so interesting.
Yeah, I mean, if you want to bring it.
Another interesting paper by itself because it says more the data issues that they solve rather than particularly fascinating.
The ethical and things like that.
It doesn't deep.
Okay. I'm gonna end the call now.